and Part Failure Solutions, sponsored by Cimatron Technologies and hosted by Metal Forming Magazine. My name is Brad Cooven. I'm the editor of Metal Forming Magazine, and I'm pleased to serve as your moderator for today's session. Since today's go-to meeting is being recorded for archiving, all participants are in listen-only mode. The speaker and other listeners will not be able to hear any audio from your site during the program. I do want to let everybody know that a link to this recording will be available within the next few days on the websites of Cimatron and of Metal Forming Magazine should you want to share the recorded webinar with others. You do have the ability to communicate with us throughout the program by submitting any questions using the question box, which is located in the lower right-hand control panel. Simply type your question to an organizer as selected from the drop-down menu. At the end of the presentation, we should have some time left over to take your questions. So now it's time to begin today's webinar. Joining us as our presenter is David Lindeman. David is an application engineer with Cimatron who's been in the toolmaking industry for some 30 years and has vast experience in design, CNC programming, and machining. Please welcome David Lindeman.
Thank you, Brad. Appreciate the introduction. On our program today, we're going to look at particularly simulation and how it can show us the issues that we're going to encounter when dealing with stamped parts. That could involve spring-back issues, part failure issues where we might see the part tear. The important thing about this is we're not just looking at pretty pictures. We're not just looking at a representation that would show us either pass or fail, but it's real data that we can use to make decisions and also use to actually fix any of the problems that we may encounter. So we'll look at a few real-life jobs or some things that are based upon what we've seen in real jobs so we can understand the technique used to fix it and also some of the functionality that's available to deal with those issues. And perhaps it's not as talked about as much as forming simulation, but still it is of note that tool collision, tool motion simulation are also a couple of popular tools that can help prevent errors. And the whole idea behind this, of course, is to help us so that we can cut down on reworking the tool. So my name is David. I'm very pleased to be with you, and thank you so much that you're giving us some time and attention this afternoon, and hopefully that you'll find the presentation to be very useful for you. Just a little bit about Cimatron. Cimatron is a CAD/CAM software that's one of the world leaders in providing specific solutions for the mold and die industry. And in particular, with those 32 years of development experience, the majority of it has been focused on tool making. In fact, you'll find when you deal with Cimatron, deal with our technical support staff, that the majority of the engineers have been involved in the industry itself. We're operating in 35 countries with well over 40,000 installations, and because Cimatron is a fully integrated solution with specific functionality just for designing and building of tools, we find that our customers can get their tools done and back in the market quicker than others who are using what might be called best in class, or they'll go out, they'll buy the best NC seat, the best drafting seat, whatever the case may be. Still, we're finding that Cimatron customers are quicker in getting their tooling completed. Okay, let's talk about springback. Everybody knows about it. It's probably one of the greatest factors to turning out a good part is to be able to compensate for springback. Even an experienced designer with years behind him can find it very difficult to understand, predict exactly what springback is going to do. We know springback as the simple explanation, the metal's resistance to being formed as it wants to adhere to its original shape. But that will vary from material to material, from gauge thickness to gauge thickness. So it becomes very time consuming to check the parts and understand exactly how springback has affected it. You may spend hours on a CMM going through an array of points to see what it compares to once it's been formed. After that, maybe you've heard that nasty little term called tape and grind, where now you're going to grind away metal off the die, tape up areas to try to beef it back up, and hopefully after hitting it a couple more times and going through this process, you'll get something that's closer to what the actual finished part is supposed to look like. Obviously, knowing that that's going to happen, typically the die maker would keep the tool soft go through this process of grinding, taping, re-engineer it however best you can before he goes into making a hard tool. If that's the case, then that's going to consume some design time trying to redesign it and to match what that new tool is going to look like. The question becomes, though, are all these costs actually in the original quote? I mean, quoting is a hard enough job as it is. Recently I heard a statistic from a company called Harbor Results Incorporated. They did a 2013 vendor study, and they made the comment that typically a die maker is landing at best 45% of everything that he quotes, which means there is a lot of quoting going on. I would imagine with very little lead time just to keep up with the quantity of quotes needed to keep that amount of work going through the shop. So where is this cost being added in? Can it really be added into a quote to keep it competitive? It seems not likely. It seems that these costs are actually getting eaten up every time they occur from job to job. What we're looking at now is an example of a part that's been put through a springback analysis. If your eyes are good, you can see the red tip out there on the far end is getting close to about 18 thousandths of an inch away from where it should be. This particular analysis, just to familiarize yourself a bit with what analysis does, is looking at how much deflection would occur in this part if it were just hit at one time. But what I want to stress to you is that what we're looking at is not just an array of blue, yellow, green, and red, but it's real data that's taking real measurements. That in itself is useful, but it's also been captured data, which we can use later on. And of course, the purpose is to understand what is going to happen before we get into cutting the tool, so that we can be closer at the beginning and understand how we can eliminate or minimize reworking the tool all the time. How would I fix this? Adjusting a part to accommodate springback is a lot more than just moving surfaces around. You get the idea of that green face in this picture that has to be tipped down to deal with those 18 thousandths of an inch of springback. But it's really going to affect the entire radius at that point. That radius is going around a curve, a bend. That is going to be affected. Really, even in what you would consider this very simple part, there's some work that you would have to do to the part to model it, to get it correct. You may choose to model it here on the part, or actually with the die steel surfaces in your CAD design. Now that's if you have a 3D model. How do you fix this if this is a 2D print? You're looking at a 2D print of a die design. How are you able to capture the information to understand the effects of the springback? And I stress that because it is important to keep the prints current with the design level. When that doesn't happen, it seems that you're fating yourself to go through the exact same hassles again and again. When a part in the die needs to be replaced and you go to the print and you cut it the same way you did the first time, which didn't accomplish the springback, or if the part design changes and you have to deal with engineering changes. And I mention that because I've seen it happen. What the best solution would be, though, would be to have dedicated modeling tools specific to dealing with springback and addressing all the issues that springback forces you to look at. Now, an example of this is shown here in the picture, and yes, it's in Cimatron, and I'm doing this also for the benefit of our Cimatron guys who are watching so that they know what this functionality does, and I'll demonstrate it. It's not a matter of just picking which you want to touch and letting it flow and making it adjust that way. Really, you see in the light green, those surfaces are not going to be affected by springback, but the darker surfaces, the dark green ones, are what we're going to go after. Here I'm going along 3 points on that edge, adjusting the 2 corner points and then the midpoint right there at that very far away point of the flange. And this is a manual adjustment. We're touching those 3 points, letting that entire area flex. That would accomplish what we're dealing with in the springback. So maybe I'm okay with that. Maybe with a simple part, that's all I need to do to adjust for springback. What if I need more accurate solution? What about more points or tougher geometry? Again, I got to stress to you, this is an example of gathering information so that we can correct the model and make the changes. But there's more to the story, isn't there? What if the material is thickening in a certain area? If that's the case, then I have to worry about wrinkling. I'll have to make sure that my die is ready to deal with a thickening area? What if it's going to tear? See, all this is going on, and analysis is going to help us to see every aspect of what's taking place with this part. And with that, let me show you a little more detail what we have here with the spring back functionality. Hopefully you can see the part okay, working with inside and outside material. My choice, if I want to work with the inner skin or outer skin, basically I only need one or the other because I'm going to be factoring from one or the other in my calculation. The system tells me it's 74 thousandths thick, so right away I know I'm dealing with a 14 gauge material. I'll set the material properties now. And here you can see the thickness has been recorded for me. And I'm dealing with a typical K factor of about 0.33 when it comes to the bend. Since this is a fairly simple part, we'll just use some basic mild steel, some cold rolled steel. Now those properties are saved with this job with every type of function that we perform. I'll grab a blank, which is going to be the outer perimeter. The way I liken it is if you were to put your foot on this thing and smush it down, or one hit, what would it look like? And there would be a blank, which is a great way to get the information you need if you're quoting. But what we're going to look at now is the analysis. Here it's showing me that I could have a thickness strain of almost 10% right here in the dark blue area, and I can see from 74 thousandths thick, I'm gaining up to 80 thousandths of material in that area. But as far as its formability, everything looks good. There might be a tendency to wrinkle here. Finally, let's look at what happens with springback. And as I calculate the springback, you can see I'm really reaching a much higher magnitude out here where it's deflecting. Bring that down so you can see the tool tip. Yeah, I'm about at, what, 22 thousandths, 23 thousandths away from where I need to be. This information has now been gleaned. It's kept with the part, so we know what the springback and deformation properties are all about. Using that information, we could go forward and start making adjustments for springback. Case being, maybe I'll grab a point here and then tell it how much I want it to deflect. All right, something like that. So obviously the more points I have, the more accurate I'm going to be. And now it gets to the point where you're asking, well, how tedious is this to deal with several points? So I'd like to show you another solution besides just what we showed you here in the slide. If I hop over to this functionality, all that information that you saw, the red, blue, the green, all those are points. Those points now can be imported into this dialog box, which you see here. My choice of working with, again, inside or outside of material. I'll go ahead and calculate the points against the part. So now I know the start point, the end point, basically. And as you can see, I'm working with 3,916 points. We can save that off into a tabulated spreadsheet, an Excel file. I could either apply it to this part or apply it to the die steel for whatever station that I'm working with. Go ahead and tell you what I'll do. I'll go back and make sure I keep the original. And then we'll go ahead and calculate that. And when you look at the part, you can see I'll highlight these faces that have changed. Give it a nice little green color, and you can see how it has indeed moved away from the original position. Something of note about this too, going back to my points, you can see the wide array of points it's generating throughout the entire part. So, pretty versatile functionality for dealing with springback. Now the next question, of course, is always the same question. Does it work? This brings some real-life cases to example here. This has been changed a bit because I can't show you the original part, but the scenario, the problem is captured in what you see here. So we'll use this panel as an example of springback. Taking it into the analysis, you can see that there's deflection just all over the place, as you'd pretty much expect. It deflects as much as 1.5 millimeter in the one direction shown in red, and then 3.2 millimeters in the opposite direction. Dealing with a cold rolled HSLA 340, and it's not very thick, 9 or 0.9 millimeters, so roughly something around 20 gauge, I believe. But the overall size is pretty extensive. It's 17 3/4 by 37.5. So you're looking at a big part. That's a big piece of steel that's going to make this particular panel. So again, we run the function on it, gleaned all the points. If your eyes are good, you can see there's over 34,400 some points that went into this analysis. And then those points are all captured and then brought forward, like you see here in those little white dots everywhere. So we save those points off. Now instead of changing the part data, in this case our customer changed the die surfaces because he was going to affect the tool this way. And again, this analysis is dealing with whatever that particular metal is that we're making the part out of and its particular properties and gauge thickness. Finally, here are the results that you can look at. You can see that the die surfaces were altered, and when we took a check on it, putting it on a fixture, we found that it was 95% intolerance. So understanding that that would be about where it would be when it was assembled, at 95% good, the customer said that part will work, the functionality works. Even though 83% of it was unclamped, intolerance is still very high. And you can see the results were basically one cut, and then you got a decent part that meets 95% clamp tolerance. So 20 hours of design time was saved, and this function basically ran in about 15 minutes to save 20 hours of design time. That's affecting over 1,170 surfaces that the designer doesn't have to go back and tweak. If I'm the shop owner, I'm looking at that, realizing that saved me a half a week of design time that I could use on another job. Now, what about some of the changes that may come up? I mean, what if the customer now says, well, okay, it looks good, but do us a favor, why don't you raise this 1 gauge up in thickness? Wouldn't it be nice to know that your part would still, your steel would still work when it came to crunching a part that big? That'd be a good thing to know when you're quoting it, wouldn't it? If your die steel would still make a good part. So the results pretty much speak for themselves there when it comes to dealing with spring back. It's a big factor, but it's nice to see there's a way that you can deal with it effectively and in a cost-effective way. We'll throw a few more examples at you here. Here's another example of a dramatically bent part. I'm showing just the tail of it, which is kicked down drastically. And you can see, if just to run the analysis on it, shows me 80 thousandths of spring back down there at the very tip. Of course, it's no solution or no surprise that you pretty much don't always get to form a part with one hit. I mean, that's kind of understood that you have to do some development. All right, so what we're going to do is look at taking this part and kind of unraveling it. What would be the station that I would strike this at before taking it to its finished form? All right, so looking at this, this was a development that we did to get it to that station before the strike, and it's one of those things that actually it works out well for us. This transitional shape, when we compare it with the spring back, reduce the spring back by as much as some 20 thousandths, down to 20 thousandths. So realizing this, it helps us to prove out the process. Is this form going to work for us? Is it going to be formable? And is it going to help us to deal with the spring back issues? Finally, if I take that intermediate shape and now take it all the way to a flat blank, I have virtually no spring back to deal with, plus good formability. So you get the idea how you're in that comfortable green, showing you the minimal condition, and by going station by station, you can prove exactly how good the process is, or if there's a situation that you need to deal with. And that's going to be typical. The question is, as you build your forming stations, are you creating a condition that one of those stations that's going to make the part walk? It's going to spring on you. Do you know which station it is? And then looking down the road, is it something that you can later have a follow-up station that's going to correct that spring back? So this was an easy example because it worked out well, just by how we were doing it. And now to take it from 80 to 20 just by that intermediate station is very, very helpful, to say the least. The important thing is to be able to prove it here using the analysis before committing to cutting the tooling. Now here's another fun part to look at. This time let's look at a part that failed. And in the analysis you can see the red knuckles. Okay, so here the material tore across those knuckles. Now a little bit of history here talking about this particular situation. It was started as a 2D design, and once again I've had to change the part a bit, but I captured the problem here with this knuckle shape. I started with a 2D design, and there was no analysis done beforehand. The designers, well-experienced guys, looked at it and realized probably not going to get it right the first time, so let's make die and punch inserts. We'll harden those inserts because more than likely we'll have to remake them anyway. And this happened 3 times, so they basically scrapped 3 sets of hardened inserts. And what they were left with was realizing what doesn't work. So guess what the part would come out as being? It didn't work. Try another shot, still it didn't work. That was what you would call the engineering process. Keep making changes until finally you reach a point where you feel like the part is good enough or it actually does work. Well, about that point, after scrapping 3 sets of hardened die and punch inserts, the idea was, let's give this analysis stuff a shot here. One of the solutions that they came up with was to introduce a station before trying to form all that over the knuckle. And in doing that, the solution was to increase the size of those corner radiuses and to drop the walls down at an angle. So I'm kind of exaggerating it a bit in the picture so that you can see exactly what we're doing. Also, the part was left high. All right? So in other words, another strike would be needed to push it down to the correct height. And in doing that, we're putting compression on top of the part, actually pushing the metal out and around, in this case into that knuckle area. Here the strain analysis says it's good in green, good to go, so that would have been successful. To give you another idea, here I cut a cross section through the part. The bluish gray part, that would be what that final form would look like, and you can see the light green just kind of riding a bit high above it, and you can see the angle and also the more generous radius in there to accomplish this. Finally then, on the last strike, create the finished form. It pushes it into the smaller radius and wipes those walls down, and also most importantly puts compression on it. So there in the knuckle area you now see blue where there once was red. So we're forcing more metal in there, and a few more thousandths is getting in there to fully form that area. So the combination of a couple things to make that happen. But the important thing is we went through the analysis step by step so that we could accomplish this. I think it kind of paints a picture now when we talk about how do we get there when we're looking at parts like this that could fail. We need a couple of things. We need to have a good 3D model that we can run the analysis on, first of all. And then it's not just looking at it one time so it'll pass or it'll fail, but looking at what we're doing to the metal as we go station by station. Because very often the solution lies just in doing that and understanding, again, what each station is going to, how it's going to affect the part. We talked about 2D versus 3D. There are a lot of shops out there that are happy using 2D, and usually when I ask them why they haven't switched to 3D yet, the answer is because they already have 2D. And they've been using it, they've got a mastery of it, hey, it works for them, right? The thing about 2D, as the example here shows, you're limited by what you see. Whether I'm looking at a 2D print of a die design, or if I'm looking at a CAD file with multiple layers, all drawn on the same plane, maybe use standard like blue is the die steel, green is going to be the punch steel, red would show you where the part or the strip is at. Still, looking at it, can you find where the part interferes? This again is a real job that was tooled, but it had an interference that created a problem on the finished part. So if you found it right here with that little hidden line, you guessed right. what you have here is a V-block where the part actually extends just a little further than you might see at first, and the edge of the part rolled into the radius at the bottom of the V-block, causing it to curl up and around a bit. 2D stuff like this just doesn't allow you the opportunity to have the system look for interferences, and that can create some issues. Something like as simple as detailing out your punch steel, your retainer steel, putting in your dowel pin locations, then going back to the die set where you're going to locate it from. You put in the dowel pins. Now you go and print out two separate prints, and lo and behold, something happened. Now the dowel pins aren't lined up. You know how maddening that can be after you've gone through the process of wire EDMing out your clearance, and then wire EDMing the dowel hole, and now they don't line up. You know, things like that are so avoidable with the 3D system that allows for good collision detection and that allows for the part to be checked. Here's what it would look like in 3D at the bottom of that V-block. The bold red line here, as run through an interference check, tells you right there that's a part that's going to curl, that's going to fail. And that, again, can't stress it enough, needs a 3D model to do that. So I ask you, which is more expensive, the designer's time to catch that by running a program that takes 5 minutes, or the die maker's time? Now, a die maker can look at that and say, you know, that's not like the end of the world here. This really isn't the most serious mistake. You can go in there and grind that right out and get your clearance. True, I would call it more like an embarrassing mistake rather than a serious mistake. I mean, if the designer were to catch that, everyone would think, boy, he's a genius with this 3D spatial ability to see things when it comes to looking at a print. You know, the problem could be, though, it means you take the part out of the press, you have to take the detail out, you're going to have to change it. Now what happens if down the road you need to replace that V-block, you go back to the print, you're in a hurry, so your shop foreman says, oh, let's just kick that on the side and put it in our wire EDM and burn it out. Well, the corner is still going to have that radius, and it's going to do the same thing again. All right, so having the system integrated where the prints know what's happening to the parts and where you can see the changes and keep those changes is definitely going to save time. As far as the argument goes for grinding that out, one of the shop foremen I worked with would have told you, yeah, you could do that, but while you're at it, why don't you carve your initials into it too so everyone knows that that's your handiwork. It just makes sense to try to do the best we can to avoid situations where we'd have to rework a tool, especially if they are so easily avoided by having good functionality available. Let's talk a little bit about some other things like die motion simulation. It's very nice to have that. Let me pop over to a picture so you can see a movie. Hope that shows up. It is handy, and it's becoming more and more useful to be able to do this and looking at how your die motion is going to react. You may actually crack up here when I go back to the PowerPoint real quickly. When I look at point number 4, does the pilot enter first? The person could say, if you have to ask that question, then you're not dealing with the real die designer. I mean, that's just basic 101, right? But isn't it nice to know that there's a way you can check that to make sure that a lot of other things that are important are also taking place? Like, does the strip clear when it's lifted up over the forming areas? Does the stripper plate have enough stroke when it comes down to hold the part down before the die or the punch is disengaged? Or does it have too much? Is it starting to over travel? Maybe if I'm using a ball bearing cage on my guide post, I'm going to keep that bearing inside the guide sleeve. Like what I'm seeing here, I'm disengaging. Things like that can help us to make sure that we've bug checked the die before we go and try to enter both halves. Now, when you think about right now where we're at in the die industry, I could tell you that I know a lot of guys who are designing who are just starting out, and it's because what's happening is that shops, lacking apprenticeship programs in their area, are hiring kids and trying to teach them the trade, the industry, hoping they'll catch on and hopefully they'll stay and not get stolen. One statistic I'll quote from Harbor Results Incorporated again, their 2013 vendor study, says the average age of a die maker now is 56 years old. So I'm feeling good. I'm 48 and I'm feeling like a kid again. But at the same time, it helps you realize that They're lamenting that it seems like an entire generation in manufacturing has gone off to do other things. There's a gap in knowledge. At 56, how many of them are going to retire in a few years? To have the tools that help you understand everything that's going on in a die really is a crucial thing to not only educate people, but also to make sure you're double checking everything as you get into like your die reviews. Alright, well with that I've got one more thing I'd like to show you. Let's talk a bit about kind of putting all this together into a strip. We'll look at some analysis tools, we'll look at some techniques, functions in the software that will help you deal with spring back. Here I've got a simple bracket with some upward forms being made. So I'd like to just kind of quickly go through how all of this helps us in understanding what go into building a strip on this. So copy that over basically. I like to work with the inside of material. Again, I've taken the measure at 14 gauge. Let's get material properties that we want to work with. And just because it's a simple demo here, let's keep that at mild steel. Okay. Now if I take a look at what's going to happen with the part in terms of formability, go ahead and calculate out what a blank would look like, and then let's look at some analysis on it. Well, it's not thickening at all. I mean, that is very, very formable with those easy bends. Safety zones are a piece of cake. And then when I take a look at spring back, bam, I see all kinds of red. As much as, again, 80 thousandths down here on this very end. So I do know I'm going to have to deal with spring back as part of the issue and how I go about unfolding this part. All right. First technique I'd like to show you is I think of it as unraveling the part. I've used that term before. And you'll see how all this comes together when we start to lay a strip out. All right, let's unbend this particular feature right here. All right, again, my K factor, all that is based upon what's in the system. My choice of either working to a flat, or maybe I'll kick that out to a 45-degree angle and I'll let that radius drift a bit. So that's what the result looks like. And if I put this in a side view, the other side view, here you can see how it's kicked away. Now when I come back to do my finish form, I'm going to be pushing down on this and forcing it into that die form to capture that. So that's one way I've seen done quite a bit to deal with spring back, that second hit like that, and changing the radius. Let's go ahead and make these go to a flat now. So let's say at this station we'd flatten that upward. And then coming over here I have a different kind of bend. You can see that that's changing the size of the radius, so that's not going to be a straight linear bend anymore. And as I unbend that, I also want everything here to roll up into position. All right. So there you see that has taken shape. Continuing further along, we'll go to a next station. Perhaps here I'm interested in just taking those tangs down to flat. And we'll use another local blank function. On the right you see there's several different types of functions for different type of bends. Maybe I've got something very complicated and I have to create a form that I need to unbend that part to, instead of just a flat plane like I'm doing now. The blank unbinder functionality lets you pretty much make whatever you need to make and then see what the metal form would look like if that were used as your binder or as your catch surfaces. Might be another way to express that. Now we'll go back over here. Again, since I know I've got spring back, we'll go back to this moving center. Maybe here we'll kick that down to 35 degrees. Did you notice it first said 60, so it knew what the angle was that I was starting at to get to that right position by the time that I have that bent upward. Maybe we'll do something similar to that. And then in our last shape, let's take this all the way to a flat blank. And again, I like to use this version of our blanking tool. Try that again. 1 second. Need to zoom up on it to get a better pick. Okay. And every bend again is based upon the properties of the material. Let's now grab our perimeter, our 2D shape. One more thing, please. Make sure this is all one coherent sheet, and then we'll grab the perimeter of this part. And that'll be our unfolded blank then. Because I have progressively worked through each operation of the unfold, this blank that I'm resulted with now is going to be more accurate than when I first hit the part and did the blank. That part originally, like when I did that, was like putting a foot on it, smushing it down, going to flat, right from center. By controlling each unbend, I've much more imitated what the process would be like. All right, let's start laying this thing out now into a nesting pattern. Your choice of, flip to the top view quickly. Your choice of how you want to work with this, left to right, right to left. As I interrogate the part too, I'm going to keep track of my scrap area. My progression is set at 3.15 based upon a minimum distance here. Maybe I need more room because I'm going to put a pilot right in the middle of this part, right on a central carrier. 1 row, 2 row out. I'm just quickly brushing through some of the functionality just so you can see how there are dedicated tools here just for laying out and designing dies. Next, as I look at this, I'm trying to get an overall view of how many progressions I'll need. And I've looked at maybe 5 different forms I've made. So within the 3, guessing at about 3 trim punches and 5 forms, let's make our progression set at 8. Let's also set this so there are no margins, so that when I order the coil, it will match the finished part, basically, like that. They could put a start margin in here as well so that I have room to position a pilot hole. Now, very quickly, we'll just start sketching in a carrier. I'm going to use just a minimum of information so that you can see what we're doing. Everything can be changed on the fly, too. And then how big do I want the pilot? And then I'll make sure I've got that center. Like I said, my pitch was 3.75 divided by 2. And then also, let's capture about where my punches are going to go. I have 2 punches that would extend out into the stock guide area, and I'm just going to eyeball those in for now. So, one more thing I would like to do, since I've got this shape here, is drop a punch in there first before I roll the edge up. Okay. Now affecting the strip, first thing I probably punch, as anyone would do, is the pilot. Tell it the first position, and then it carries on down the strip. So we're working at a top view, so you can see exactly what we're doing. And now I'm just going to be snatching some of these shapes and punching them. Punch that. And we'll punch the other one down here. Perhaps I'd wire EDM that and just use a standard punch retainer. Let's also do the middle section right here. That I put on a simple punch pin. Probably want to get out of the Danley catalog or something like it. Now I've got 2 big wire EDM punches. Because real world, I'm going to do something about this. I wouldn't want to put all that on a single punch. So just so you know, I haven't completely lost my mind here. And then I'd also, as we go, we can add chamfers, add radiuses. We also can use cookies, which are very nice for extending a notch into the side of material so that I don't have a shear on shear condition with 2 punches. And Let's say we punch it here. Like you see that, again, the trim is it's updated throughout in our strip. One last one to do, and this is by far a much better looking punch, but we'll go ahead and again add the radiuses. All right, and finally punch that, and we'll just shift it over one right to here. Okay, so finally we'll add in the rest here of what I've done on my strip. And now it should start making sense to you why I unfolded the part backwards and how I'm using that information on my strip. Of course, I could add more stations if I wanted to or needed to. Maybe I need to put some idles in there. Maybe I need to rethink how I'm going to do some folding. Maybe there's one I want to kick over in 45 degrees. All that is stuff that you can now deal with quite successfully. And then this particular feature, where I've got this radius. Let's use this and stretch it in. Maybe right after I hit my first punch here, I'll now go ahead and form it right here. And I only need it on 2 occurrences. We'll go ahead and trim that. Now that is a feature earlier on in my progression. So I wanted just to show you briefly some of the dedicated tools for forming, for doing unbends, for laying out strips, nesting, all those important things, the decisions you make up front, whether it be in quoting or in actual die design. And I hope you got an idea too of how quickly you can go through this, get information, make the decisions you need to make, and get moving on with your design. Again, just to review, the things that we say are most important, trying to keep business competitive is avoid costly rework. Avoid mistakes that are so easy to diagnose and debug. Why put that in hard tooling if you don't have to? You can do that by better understanding what's happening to the steel, what's actually happening to that formed part as we're making our decisions about how we're going to form it. To some measure, by no means complete, of course. Some of this functionality I hope I showed you can, to a degree, compensate for the lack of experience, and that it can help make some mistakes more obvious and catchable. But importantly, the whole idea is to speed up the whole process, speed up the design time, speed up the time it takes to build tools, and avoid all those mistakes. So yeah, thank you for your attention. I hope that I've given you something to look at that's interesting and useful to you, at least get you thinking about some of those important matters that we all have to deal with in die design. Well, I guess with that I need to give the microphone back over to Brad. I think we have questions to look at.
Yep, thanks, David. Very good. We do have some questions, and we got a little bit of time left. One person would like to know about any specific applications that you can think of where some of this has come into play in aerospace, particularly for tightly tolerance, like 10,000 tolerance parts in the aerospace industry. Anything come to mind specific to that?
I do know of guys that are having to form that tight, and medical as well. And yeah, it's tough because anyone can tell you even the parts coming off the coil are going to differ from the beginning of the coil to the end of the coil. So there is a constant eye that has to be kept on the process and checking. So with that, knowing and getting that middle result is very important so that your bend is as close to tolerance as you can possibly get it. And I've seen good application to it. Let's see, in particular part, I'm not even sure what that part was I looked at, but I know in medical, it's a lot of little small parts. So we're talking about keeping a good shear.
Yeah. How about on the aerospace side of things?
All I can say is I've seen it done, but I can't tell you what the description of the part was. To me, it was a bracket.
Okay.
You know.
Yeah. Right. Okay. Your software works with SolidWorks, correct, and some of the other CAD?
Yeah, we have a number of direct translators for a lot of modeling systems.
Right.
And then, as always, we can take standard like STEP, which is really good anymore.
In the case study number 3, which was the knuckle part, um, what is the size of one of those knuckles, and what is the material type? Are you allowed to describe what that material is?
Yeah, the material is actually a mild steel, but the knuckle, that inner radius, was at about 90 thousandths. So we had a time just making sure we got a small enough cutter down in there, you know, to get the form. That's the outside surface was at 90 thousandths.
Gotcha.
So because it was so tight, it really was, you know, that back up and down was a real problem.
Okay. What do you see with the typical training time for a new customer? The question is, it seems that your software is pretty user-friendly compared to some other software that's being used out there. So what do you see typical training time from your customers?
Oh, say starting from scratch to make you know where all the functions are at, this basic modeling even, usually that takes about a week of training. Then it takes you a couple weeks to feel good at it, you know. Then we can get into the more advanced functions. So we've seen guys become productive within 3-4 weeks. One thing that does help you a lot is, especially if you're doing like a die design thing, the terms on the pull-down menus make sense to what you're trying to do in the die. It's not some obscure CAD function, you know, but it's more like the process you're going through as you're trying to do it. So that does help.
Right. So this person wants to see an overlap of a flat squashed pattern versus the one that was developed after the stations were designed. Is that something that maybe you want to handle offline with this person?
Yeah, probably would need to. I would, that case, it sounds like they have something in mind. I'd like to actually work with the part then.
Yeah.
So
your last slide, right, has your email address on it?
Oh, yes.
You want to switch to that one? Yeah. So there's David's email address. If Adam, you'd like to maybe get in touch with David offline, that would work out good. Does the software work for forming and bending of closed or tubular sections?
Ooh, yeah, that's tough. I could say yes, but I won't tell you it's magic. You have to finesse it. Okay, so I've not, again, I would be like, let's look at what kind of tubing you got, how much you're bending it, and what results are that you need to get to. From what I've shown you, you can pretty much see we're dealing pretty much with prog die intended parts. I've seen tubular parts laid out in progression, and it's worked nicely, so I know we can do it.
Okay. So this is a term I haven't heard before, but maybe you know what this means. What about Kentucky windage and injection mold?
An injection mold?
Yeah.
There's Kentucky windage everywhere, right? Yeah, I can understand that. It's pretty accurate, though, as far as the forming goes. What they say that was like 0.7% accurate to the blank. So you could put your own Kentucky windage in it. Like I could see myself redesigning some punches just to make them more stable, better tooling condition, you know, and letting it kind of free itself as it forms, if that's what you mean. But as far as like, is there a fudge factor where you do one part, it's going to be one way, you do the same similar part, it's going to be another way. It's very consistent.
Okay. Well, we'll see if we get a follow-up question for that one. Software for forming simulation, is that your own, or are you using somebody else's plugin?
We use FTI. They're out of Toronto. It was their product,
right?
FastBlank, yeah.
Yeah, right, that's right. Okay.
But we're very partnered with them, very integrated, so that you wouldn't even know, really. Seamless.
Okay. Springback, are we compatible with parts that are formed on press brakes?
Yes, we could do that. Yeah.
And I assume you can then model heavy armor plate, right? I mean, any type of material as long as you know the properties.
That would be it, yeah. And those properties, we can add more to it, you know. So we just need to know your properties of that material, and we can put it in the database.
Right. How is springback being calculated within the software? Are you running a numerical analysis? And what material properties do you consider in the calculations?
That's a good one. That's definitely a technical one. We're using this, there's a solver out there. It's the one actually that most like crash form simulators, all those are using. I can't think of the term for that. In fact, or they mentioned it at the show that we were at in Rosemont. But we're using that same one because it's in FTI. Okay, so it's that solver. I wish I could remember the technical term exactly for that.
Oh,
Then it would
looks
answer
like
the question.
Ralph chimed in and said LS Dyna.
Yeah, there you go. That's it.
That's what you're using.
Yep.
Thank you, Ralph and Wally. So we answered that question. Draw dies, can you do draw die sim in development?
I can design them, but I wouldn't say there's like a magic draw die function. I mean, I'm still going to have to pick my reduction diameters, you know, and work with it that way. Once I change that diameter, get my new height, make my percentages of changes in diameter as I work along. But I can look at it station by station and see if the material is going to work for me, or if I'm going to create a necking condition, something like that. That shows up in the analysis.
Okay. Question about R&N values. Are you actually establishing R&N values for materials, or are you using what's in the database, what's in the library?
I've typically used what's in the database. You can adjust that too. I mean, especially some thin grades, I've seen that go 50%. You know, so it's up to you. If you know better, yeah, you know what you're doing, go ahead and make the adjustment.
Right. Okay, and you can add more materials to the database or to the library, right? Than they come with the software. Okay.
Yep, absolutely.
Okay. And the software supports full die design in addition to simulation?
Yes, exactly. So, yeah, you can pull your wire punches. It's got full cataloging for all the Danley and Dayton punches and you name it, guideposts. You can customize it too so that it's typical of the die sets you use with the typical components. You can start at the beginning by just dropping the die set on, match it to your overall length and width of the strip, and then have that strip with clearance fall right between your stock guides, and away you go. So it's got some good design functionality that I didn't get into because that's a whole nother webinar.
Right. So that's the webinar. How does the software help with the quoting process?
With the coding process?
Quoting process.
Quoting, I'm sorry. Well, I think you can see how you can quickly get a blank so that you could quote just your perimeter. And if you're using formulas based on that, you can use that. But at the same time, we have a full integrated quote package that will let you go as far as estimating NC volume time and finishing time, actually looking at die pressures against your punches, or you could just drop in your components out of a database, so no matter how far you want to go calculating it versus how far you know already that you want to work with it. A good example was like if I throw a die set on a strip that I've developed, I'm going to quickly get my overall steel sizes, and maybe that's all I need to get my material pricing. So that quickly you can start generating cost. So yeah, even with all the formability and the tooling stuff, it can get some real data to quickly generate a quote.
Right. Very good. Any other questions? Can the software simulate dual material blanks? That's an interesting question.
Yeah, we can have a 2-out with 2 different parts.
Yeah, I'm not exactly sure what he's getting at with dual material. Do you think he means
2 different
like
materials?
a custom blank, like a tailored blank maybe? Or are we talking like a layered material? We'll have to see if Henry wants to elaborate on his question.
Yeah, that would be a good question.
It could be like those layered materials used in cookware.
Oh, sure.
So he says different materials. But again, I don't know if it's layered or if we're talking tailored blanks.
Exactly.
Have you seen applications within your software for tailored blanks? He's talking about layered materials. So
layered materials.
About that. Yeah.
To be honest, no, I haven't ever run into that where I was actually working with a customer doing that. But I got to think that once we know the properties, however we may need to modify it to accomplish 2 materials, that's going to be interesting. But I know I can adjust it to get there.
Mm-hmm. Yeah, right. Once you know the N value and the R value.
Yeah.
Okay. Any other questions for David? We're just about at the end of our scheduled time. Okay, terrific. Well.
Okay, thank you, guys.
Very good. Thank you, David. Thank you, everybody, again for attending today's program. We hope you found it to be a valuable experience. And again, please remember that an archive recording of the program will be available on our website and Cimatron's website very shortly, so you can review what you learned today and share it with others. When that is available, we will send you a link via email so that you can connect over to that archive presentation on our website. So you may as well, you can go ahead and close your browsers now and have a great afternoon. Thanks.